We all know that technology has transformed the healthcare sector, improving people's well-being and quality of life. But still, there's a lot of room for innovation and improvements. There is a medical device that's used daily in every hospital and is crucial for patient care, yet that device is full of limitations. The one we're talking about is the patient monitor. Vital sign monitoring is a common practice in patient care that aims to detect and diagnose medical problems through tracking changes in patients' health conditions, like irregularities in heart rhythm and breathing activities. Although the traditional vital sign monitoring methods used in clinical settings are generally accurate, these methods require direct physical contact with the subject's skin through electrodes and cables. This direct contact imposes several limitations, and it's even not suitable for some patients. For instance, patients who suffer from skin burns, with 30,000 people daily suffer from new burns worldwide. Many of such are severe burns that make it difficult to use conventional stick-on electrodes, and invasive or painful methods would usually be used instead. Patients with sensitive skin, where 2% of the population, which is more than 160 million people, would suffer reactions due to the electrode's adhesives. It could cause rashes and might even cause burns, especially in the case of infants, whose skin is very delicate, which makes attaching the electrodes difficult. Also, physical contact increases the risk of hospital-acquired infections. Finally, this setup is typically bulky, constrains the subject to the location of the monitor, is generally costly, and requires professional training.
These drawbacks motivated the search for a vital sign monitoring method that does not involve direct contact with the patient's skin. Our motive is to develop a real-time system that measures vital signs in a non-contact manner, both accurately and continuously. We've made a survey to ask medical and non-medical people about their experience with the traditional setup and how open they are for the alternative we aim to develop, where over 300 people from different ages and genders took the survey. For instance, we asked the non-medical respondents whether taking off their clothes and attaching electrodes bothers them, and the vast majority confirmed their discomfort. As for the medical personnel, we have asked whether the traditional method wastes time and needs professional training, and if they would trust the results of a non-contact alternative. The responses came positive and they were open for a non-contact device for monitoring. We have carried out market research and studied the existing solutions. We found that most of the existing solutions are still in the research and development stage. The researchers investigated a lot of different methods and sensors, including RGB and thermal cameras, visible light sensing, and radar. After doing extensive research of the various technologies that have been investigated for this purpose, we decided to use radar technology, where we used millimeter wave, frequency modulated continuous wave radar, a sensing technology that has been used in multiple published research and has proven accuracy for measuring some vital signs. In order to utilize radar, we had to study and understand radar basics and all the needed physics for this purpose.
Afterwards, we designed the system and planned out its execution. Our system targets the heart rate, respiration rate, and the electrocardiogram. It has software and hardware modules. The software includes the heart and respiration rate module, ECG module, and the application layer that sends a command to the hardware to estimate and display the vitals. The hardware module, in which the software one will be deployed, consists of a Texas Instruments radar sensor, a Raspberry Pi microprocessor, and LCD for displaying the vital signs. Unlike most of the research which uses traditional digital signal processing, we explore employing deep learning for extracting the vitals, where we train our models using a public dataset for the heart rate and respiration rate module. As for the ECG module, we have contacted the authors of a paper and gained access to their dataset. We have also contacted doctors at various hospitals, and we are in the process of collecting our own dataset, where we plan to do several experiments exploring the distances and angles of the sensor from the patient. We will collect raw radar data against the ground truth from a traditional contact method monitor.
The hardware module is developed through modern embedded system tools, where we will use our own custom Linux distribution as an operating system. This is our current progress. We are currently working on improving our initial results for the heart rate respiration rate module, as well as developing the electrocardiography module. Once the heart rate respiration rate module is done, we will deploy it on the hardware and do an initial test for the system. This is our initial prototype. It includes a holder that we have purchased. We designed and 3D printed an extension to it to ease the sensor and LCD attachment. The holder has an end which is used to carry the sensor and can be moved in all directions. As you can see, the distance can be easily controlled, as well as the angle of the sensor to the subject. The LCD is fastened to the holder and can be moved around as well. We believe that our system, with no skin contact, no risk of engagement or patient discomfort, no infection, as well as no need for professional training, will streamline several operations in the vital sign monitoring field. Have such a device will surely support medical personnel who need to make rapid decisions in emergency situations, and also facilitate monitoring for subjects in home care and in vehicles.